Hello, hackers. Thank you so much for joining me today. In this workshop, we're going to be covering the nature of code, Chapter 2, Forces. And I'll explain what that is in a little bit, but let's hang out here for just a bit while we wait for everybody else to pile on in. If you've seen any of my previous streams from previous GHWs, you'll know that this is a reoccurring series. We've only gotten to 2 chapters so far. Let's see how far we can get today. And if you tuned into any of the workshops that, if you tuned into any of the streams that I've done this week, you'll notice that I'm still wearing the same hat. So I remember I wanted to start today's stream by going on a little side tangent to see if anybody can guess what this bit of this cap is for. Because it's a really funny location because it just kind of sits on the side of the hat. So it's like, oh, what does it cover? I might need to actually remove the virtual background. Let me see if I can do that real quick. Visual effects. Okay. So yeah, there's like a little button over here. And I only recently discovered that this had a purpose, a previous purpose. But it's just so funny having like this little flap thing here. On this hat. So yeah, I would love to see some guesses in the chat on what you think that is for. While we wait for everybody to pull up. Hello, and welcome. Oh, I guess while we're waiting for that, feel free to also check in over here the code. It's also going to be on the QR code in the top left corner of the stream, or I guess like right above where my camera is. And also it's already posted on the Twitch. But yeah, there's a really funny side tangent because when I first got this hat, like I guess there's this like Russian warm hat that's called a Yushenka. And so looking at this hat in the store, I was like, ooh, this looks kind of like a Yushenka. Like this, it didn't have the same pattern, the ply pattern that this one has. And then so, yeah, I found out that there's an American version, American Yushenka. I think this is just called like a hunter's hat. Or maybe my Google foo is pretty bad. Yeah, there we go. Trapper hats. Or I guess it's also still called a Russian fur hat. But yeah, anyway. There's these little side flaps, and I was really curious as to what these things were, like right here. I found out that it is indeed, I guess, like a leftover from the pilot caps. Old pilot caps, or hats. And so we've got these old hats over here, same kind of design. And the really funny thing is that these were, I guess, like, optional hangups because there used to be a big hole here so that people could fit their what's it called, like radios, the headphones on the side of their ears. And so whenever they weren't wearing the rest of the headphones, you could just close this thing and it would sit and settle down and cover that hole. But we don't really have a need for that since communication devices have gotten so much smaller and they could totally fit underneath these flaps. And so they removed the hole eventually, and they've also made it so that I guess this thing just continues to stay on top of these hats. So yeah, I think the term for this, where there's like an old part that is no longer useful but still persists and continues, it's called a vestigial structure. And usually this is actually borrowed from biology. But it's also used in clothing. And so this is like an example of a vestigial design in clothing where the original use case is no longer useful, but it still remains, partially because of the visual identity or for the aesthetics, whatever the case is. I'm not really sure what Google is pulling up over here. It looks like it's just the word vestigial on clothing. But yeah. Anyway, let's get back to the topic at hand. We are going through the Nature of Code textbook. And this is a textbook series that's written by a professor at NYU, and he runs a programming channel that's called that's called The Coding Train. And so he wrote this book. It's called The Nature of Code, and its goal is to simulate natural systems, and he does this using a wonderful library, graphics library that's called processing, or the P5. Sorry. P5 is the JavaScript library made by the Processing Foundation, which also creates, I guess, like animation libraries. So yeah, we're using this because it's the same one that I guess Dan Schiffman wrote. If you would like to, I guess, like catch up, because this is part of a series, you could check out the Nature of Code I guess, like video series here, and you can also look at the MLH YouTube streams. MLH, if you want to see any of the previous streams, they are all available here. So yeah, even though this is technically a continuation, do not worry, we're going to be going pretty slow. I guess we treat every workshop as if it is an introductory workshop anyway. So don't worry about missing out on things. If you do feel like you want to go and check out the other contents, the Nature of Code textbook that we are doing everything from is also available in the Discord announcements. So yeah. Yes, it is a really nice call out to, I guess, the old pilot caps with the little flaps. And I appreciate the love for P5. Yes, we do love P5. It is a glorious library, a very handy one. I like to go to it to make a lot of my visualizations. Okay, so let's get started. All right, if you want to follow along, let me also dump this textbook link with the specific chapter we're on right here. Now, I'm not going to be reading this word for word. I'll be skimming and summarizing, I guess, like paragraphs as we get to it. That way we can get to the fun part of actually running through the exercises themselves. So yeah, let's get to it. In chapter 1, we were working on introducing vectors to move things around. Let me see if I can actually pull out the thing that we made from the first, oh, it might have been this one. Oh yeah, here we go. Basically, we started animating circles, just literally any shape that we wanted, and we chose circles, and starting to add some sort of acceleration to it. So it is only natural, pun intended, that the next step is to, I guess, like start combining different accelerations in the form of forces. And so there's a few fun forces for us to play around with. And we're going to be looking at simulating gravity and wind. So yeah. We're also going to be building, it looks like, a very simplified version of a physics engine. Physics engines, of course, I guess if you've taken any physics classes, you'll know that there's tons and tons of forces that we need to consider whenever we look at any sort of frame of reference. When I say frame of reference, I'm talking about any context where a particular force may be acting on an object in order to influence how it behaves. So yeah, we're going to be focusing on building something that is not too heavy in the code, because otherwise it's going to get really unreadable. I'm not going to really talk too much about this just yet. We're going to continue looking through the textbook. So let's keep going. All right. What does it mean to be a force in the real world? Just like the word vector, forces can mean a ton of things, but the definition we are going to be rolling with is it is a vector that causes an object with mass to accelerate. And as a quick recap, we know that vectors are, it is something that has both magnitude and direction. And so a force is just something that pushes something to move faster and faster and faster. Okay. So then we have Newton's famous laws. An object at rest stays at rest, while an object in motion stays in motion. And it is, let's see, Dan proceeds to expand the definition by saying that there are unbalanced forces that can affect these things. And so I believe he's hinting at the idea of friction. When Newton came along, the previous theory of motion was really old. And so the definition came from observation, which I think is a pretty common theme within the world of simulating natural systems. In order to create a model, you must first observe what is going on in the world and then create a theory on how everything works together. As Newton established, in the absence of any forces, no force is required to keep an object moving. Ooh, anybody else feeling a hint towards friction? When an object is tossed in the atmosphere, its velocity changes because of unseen forces like air resistance and gravity, which slows things down. When an object's velocity stays constant when there are no other forces, meaning the net force adds up to 0. This is referred to as equilibrium. So that means it is continuing to stay at the same velocity. Okay, so in terms of the P5 canvas, we can restate the first law as an object's velocity vector will remain constant if it is in a state of equilibrium. In this example over here, I believe all of the balls are actually already at max velocity that's been assigned here. I wouldn't worry too much about understanding everything. Let me see if I can actually just hide all of these things. Yes, here we go. Here's the limit function. And so basically, if the velocity's magnitude, the magnitude being just the raw power that something is moving in, that our velocity is moving in, then we would normalize it. Normalizing basically just removes all of the, I guess, like power that something is moving in, and then, and keeps just the direction, and then we multiply it again by the actual max velocity. Okay, so yeah, since these guys are all moving at the same velocity, that means that they are in relative equilibrium since they're not moving. Okay, in other words, the mover class update function shouldn't apply any math functions unless there is no force present. We're going to be actually copying this general structure of our mover class whenever we start working on the exercise that we're going to be working through in the textbook. But let's keep on going. We haven't gotten there yet. We've got some more definitions to go through. Newton's third law: for every action, there's an equal and opposite reaction. And then another way to restate it: forces always occur in pairs. Two forces are of equal strength but in opposite directions. In other words, there's an action and a reaction. There we go. So if we are pushing a stationary truck and the truck is bigger than us, it will never overpower us, a stationary object will never overpower us and send us flying backwards. Okay, we've got some acceleration things. I'm just going to honestly just skip through to the big definitions, and we will go from there. If you calculate a P5 vector called F that represents a force of an object on an object B, you must also apply the opposite force that object B exerts on object A. You can calculate this other force as P5 vector dot molt force 1 and then -1. So we're just basically multiplying by a negative vector. That makes sense in order to apply the opposite force. It's often not necessary to stay true to this law, such as the case of gravity when we're simulating that. But if we are going to, oh, sorry. Okay, so yeah, he's basically saying we don't actually need to apply Newton's third law to every scenario because some models simply don't need that, I guess, like accuracy because it doesn't actually affect any part of the simulation in any meaningful way. Or we just don't need that level of precision. I think that's a fair point. So let's see, and then we've got Newton's second law, which is force is equal to mass times acceleration. Very classic definition right there. We've got a little aside here to talk about weight versus mass. Mass being the raw amount of matter in an object, and then weight being how much that mass is weighed on with gravity. And we've also got density. These are all, I guess, like key terms that we can simulate. I believe we'll be getting to that soon. Okay, so finally, some good code. Let's see what the context is here. Looks like we're basically just going to be taking our existing class and then adding in another attribute right here. So let's go ahead and start doing that. I'm going to take this fresh P5 file. Let's see. I had kind of prepared this for the first exercise, but let's actually just go ahead and make a new file. But before I do that, I'm going to do a quick tour of this workspace. If you want to follow along, the link is available once again on the Discord announcements, but I will also be sharing it here. If you want to log in so that you can actually save what it is that you're doing, you'll want to go to the top right corner and it'll probably say something like log in over there. I'm already logged in. I log in with my GitHub account. I think that's very helpful if you want to keep track of your progress. So let's see, starting on the top left, we've got the play button. So this actually runs the code that we're running, or the code that we have down here. We've got the stop button, so if we stop it, nothing is going to be drawn. We've got the title over here and its publicity. These other things aren't too important, but for debugging, our console is down here. P5 is a JavaScript library, which means we will have access to all of the JavaScript functions if we need to deal with that. If we click on this toggle arrow, we can open up this shelf over here, and we'll see we've got 4 different files over here. There's nothing inside Balloon really, because this is just me getting ready for the next exercise, and I got a little ready before we got to the example right here. But everything basically lives inside an HTML document, and this is what's going on over here. If we just hide the head, we can see that there's really only one main thing inside the body, which is the main element, and then the script that pulls up right here. Now, the way that P5 works is it looks for wherever the main document is inside of our HTML file that it's attached to, and then it just attaches a canvas element, and that is the thing that we actually draw on. And so if we look inside sketch.js, we can see that we've got 2 functions over here. We've got one that's setup and one that is draw. Now, if you've done any sort of hardware programming before, such as programming with like Arduinos, this format may be pretty familiar to you. Hang on a bit while I plug in my laptop. Basically, setup is a function that runs once at the very beginning, and draw is a function that runs every frame. And so this thing runs all the time, and this thing only runs once. So if we want to create something that is animated, we will probably want to draw it or put it under draw. But if we want something that just wants to sit, or I guess just like run once, then we'll want to put it under setup. There is technically another function that we could toss in here, which is like preloading. If we need to preload any like assets, that's not something I think we're going to be dealing with today. So let's keep on going. So we've got this mover class that we're going to get set up with. So I'm going to go ahead and add in a file that's just called mover.js. And to make sure we can actually get something that shows up when we want to, I'm going to go ahead and add the scripts to our HTML file, mover.js. Toss in script right here. Okay, so nothing to show just yet because we haven't done anything with it yet. Let's go ahead and copy in this right here. Oop. Bad copy pasta. Create vector. Acceleration. Okay, cool. So in previous streams or in earlier parts of the textbook, we went over what the create vector is. Basically, it's just a object that has access to a few functions that's related to, I guess, like vector math. So we have access to like vector multiplication and addition and subtraction and division, which is all very helpful in helping us move directions. And then, yeah, it also has the attributes of, what is it? It's X, Y, and Z, I believe. And so if we wanted to have a location, we could just create a vector that has, I guess, like, well, I guess they all start from the origin points. This is actually, I was about to introduce the coordinate system, but let's actually get something on the screen before we actually talk about that. Okay, so our goal is to be able to add forces to the object with code like this. We've got mover.apply force wind or something like this, apply force gravity. So we want to be taking in some sort of parameter. That is the thing that we give to the function. And we want that to be giving us, I guess, like some sort of force or acceleration. So what we can do is we can create a new function. It's just called apply force. And then we're going to take in something that's just called force. Now looking down here, now here in this case, wind and gravity are vector objects. According to Newton's second law, we would need to implement apply force method as follows. This dot acceleration is equal to force. Okay, this makes sense if we are just looking at Newton's second law. However, this is a big problem because when we call something with wind and gravity, the object's acceleration is now assigned to the wind vector, and then when we try to apply a different force, it is now assigned to the gravity vector. So we don't actually do the combination of vectors. We only take whatever the most recent thing is. And so we've got a logical error, which is an error that we won't be able to see in the console because things just aren't behaving the way that we're expecting them to. So what we need to do is we need to find a way to accumulate force. And I have a sneaking suspicion that that is going to be by multiplying forces to the existing acceleration as opposed to replacing the existing one. Net force is equal to mass times acceleration. It is the sum of all forces divided by its mass. And so we can take this to update our function. This dot acceleration dot add force. I guess I was saying multiplication. I should have said addition. Oops. Okay. Force accumulation has more than one piece. Since we're adding all forces together at any given moment, we need to make sure that acceleration is cleared before each time the update function is called. And the reason why is the gust of wind is still being in effect. Yes. Okay. So forces are the things that continue pushing things along, but if a force is no longer acting on it, then we need to actually clear the acceleration, because otherwise it's just going to continue getting faster and faster as if it is actually in action. So in this case scenario, it looks like we're trying to add wind to a trigger such as the mouse. So let's go ahead and add in an update function. Let me say this dot velocity dot add this dot acceleration, this dot position dot add this dot velocity, this dot acceleration dot molt is equal to 0. Okay, so now we've got a update function. We should also technically have a draw function pretty soon. I'm thinking these functions are kind of pulling up out of nowhere. So what I would like to do is I would like to actually go back over to our vector mover and just highlight, I guess, the structure here and figure out what exactly is going on. So I'm going to start over in the sketch function because there's less code here to look at. So first thing that we did here was we created an array of movers because we wanted to have a whole bunch of them. And then we created our canvas, and then we added in and just created, or I guess, initialized our movers array with a whole bunch of other movers. And so if we wanted to make it so that the movers were, I guess, like moving, we would need to actually do that under the draw. So what we did was we made a loop that iterated through every element within the movers array to run 3 functions: update, check edges, and show. And so update is where the math happens to figure out where the circle is going to be next. Check edges is the thing that resets them once they go off screen. Otherwise, they would just continue moving on and on forever. And then we've got mover.show, which is the thing that actually draws these bubbles or these circles. Okay, so nothing too crazy over on the sketch.js side. On the mover side, we've got the constructor, update, show, check edges, and the limit function. So under the constructor, let me actually make this a little wider. First thing we did was we just initialized a random location and initialized that as a vector. And then we applied a velocity to it. We made it so that the velocity was always at 0, 0. And then we added in an acceleration, which moved it in a particular location or direction. And so let's see. This first vector just created the position. This second one created, I guess, the direction that it's supposed to move. And then acceleration pushes it into a particular direction. Oh, this is a good opportunity to actually talk about the coordinate system now. Ooh. Hello in chat. Thank you for joining. So let's pull up the coordinate system. So if you remember in math class, the way that the coordinate system we're used to using goes is we've got the x direction, which is some sort of, I guess, like direction that is constant and steady and moves in the right direction. That is still going to be true, but the thing that's going to be different is the y direction. And so as x gets larger over time, the y direction also, okay, sorry, we're not talking about this linear function right here. What we're talking about is the direction of the y right now. And so if we wanted to put like a circle maybe around here, we would need to have a positive x and a positive y. However, the way that computer coordinate systems work, at least in the context of P5, is it has the y flipped in this direction. And the reason why it is flipped like this is because when we create, let's say, like a document, right, like a document website, let's say we've got something going on up here. The only thing that we actually know how the only part of the website that we really know is the things that's at the very top, because just like in writing, when we write in like any text document, we write from top to bottom. And so if we were to, I guess, like continue doing this, then how would you say, how far deep do you think this element is from the top? That is the reason why in the P5 coordinate system, the y moves in a positive direction, going down as opposed to up. I'm not actually sure why we have it so that the y direction normally points up. If somebody in chat wants to figure out why we conventionally in math have it so that y always points up, feel free to let me know. Oh, I see a question. Are we coding in Python? No, actually, we're going to be programming in JavaScript. We're going to be going off of the Nature of Code textbook. You have all of the links available to you looking at the Discord announcements and the MLH GHW announcements. Thank you for the shout-outs. Appreciate the help. Okay, so let's move back over here. So basically, with this random direction, so the create vector, we know that it takes in two arguments. The first one is going to be the x direction, and the second one is going to be the y direction. And so if we see here, this acceleration, we've got a small x and then a small y, but they're both positive, which means when we actually multiply the force, the acceleration, it should be moving in this direction with a bias towards x, which means it's going to be moving much more to the side than it is going to be moving down. So I think if we reload this a couple of times, we'll see the acceleration start taking place, and it just kind of pushes them more to the right and then down. But also, I guess, keep in mind that this is technically random. Oh, okay, my bad. Okay, so these things aren't technically, I guess, drifting more to the right because I was confusing random with create vector. Random basically just takes a random value between these 2 points, and so we've just set a very small, like 1/1000th versus a 1/100th. If we wanted to make it so that it moved more towards the right, what we can do is we could actually just make this a bigger max vector value, and so you'll see here that the majority of them are now swinging much harder to the right. Okay, anyway, so that's that. And then I mentioned earlier that the update function is responsible for doing all of the math. So we can see here that the main math we're doing is we're just doing a vector addition. So we just add to the velocity and acceleration, and then we make sure that it doesn't go too fast, and then we add in the velocity. And so the velocity is really just saying, taking where the ball is going or the bubble is going to be in one frame, and then saying, okay, this is how much it's actually moving in the next frame. And yeah, that's how the update function works. Then we've got the show function, which literally just draws it out. So if we wanted to change like the color of this, for example, maybe we don't actually like that blue, maybe we want it to be a little brighter. This actually just uses RGB by default. So if we want like a high red value, it currently has a pretty high RGB blue value and a medium green value. So if we wanted to make this more red and blue, This would make it more of like a pink, yep, just like that. And then if we wanted to make it more green, turquoise, we'll get something like that. Anyway, so yeah, that's the show function. And then we've got the check edges and the limit, which we've already covered before. And that should get us pretty up to date. So let's pop back over to our mover function. I think for the sake of getting things on the screen, let's go ahead and set this up as if we've got our old setup again. So we've got let mover exist, and then we're going to go ahead and fill this thing in. So we're going to go for let's I is equal to 10. Let's just start with 10. I is less than, sorry, I is equal to 0. I is less than 10, which is the max size that we want to have. I plus plus. Okay, and then we're just going to say mover is equal to new mover. Mover is not defined. It totally is. That's probably because we have mover lower here than we should. I'm going to stop this auto refreshing. Okay, so now if we run this, it is still having a problem. It looks like you accidentally written mover. Let's see how we did it here. Movers equals new mover. I thought that's okay. Well, we can do that. That doesn't change anything though. Mover is still not defined. Let's see how the HTML had it. Yes, mover should be above sketch.js. So that's what we've done. Mover is above sketch.js. So mover should exist. Maybe it's because I didn't save this. Or maybe it's because the constructor doesn't exist. Constructor. Did I spell that right? I'm pretty sure I did. Yeah, spelled that right. Oh, that's because this is invalid syntax? No, it's still complaining about new mover. How curious. You know what? Instead of troubleshooting that, I'm just going to duplicate our old vector mover copy, and I'm just going to call this force mover. And if you want to have this starting point, I'll also share this in chat. Thank you for the array callouts. Okay, well, we'll come back to this one when we get to the actual exercise. So let's go ahead, pop in here, and update our update. I'm going to actually remove all of these comments. So we don't need those anymore. That's all dead code. Okay, check edges, limit is fine, show is fine. Update is fine for now. And then, actually, no, we've updated our update function. Let's add this dot acceleration dot volt 0 so that it eventually stops accelerating. This dot velocity dot add. This dot velocity. Okay, that looks pretty good after it's been applied. Okay, and so the reason why we are doing that is because, well, I guess we were getting to the exercise anyway. Apply force, this dot acceleration dot add force. I just want to see if I missed anything. Oh, I did miss something. I missed that. I missed that function. Apply force. Whoa. I need to turn off the auto refresh. Apply force, force. Okay, cool. And then this, we just had this dot acceleration dot add force. Okay, and now if we wanted to apply force, we would just pop in here, check edges, mover dot, well, actually, I guess we would need to add in, let's see, in this example, if mouse is pressed, let's the wind create vector 0.5, and then apply that force. Okay, so using forces, let's simulate a helium-filled balloon floating upwards and bouncing off the top of a window. Can we add in a wind force that changes over time, perhaps according to Berlin noise? Okay, so Berlin noise is something that was introduced in one of the first chapters of this textbook, and Berlin noise is just, it's a thing for smoothed randomness. Usually if we have random values, purely random values, it jumps all over the place. And so smoothed random values just means that the next random value is going to be meaningfully closer to where the current value is. And so that's really good for simulating things like random movements, because that, that makes it so that they don't jump as far. They move, I guess it depends on how you use Berlin noise. Let me actually just open up a previous project that had Berlin noise. Let's see. Oh, so many projects. I think it's one of the first projects we did. Maybe it's Walker 6. Here we go. Yeah, this is an example of Berlin noise being applied to a circle, and the noise is basically just saying what direction it should go. And so instead of the dot appearing all over the place, it only shows up, I guess, like in places that's relatively close to where it currently is. And so the way that we did Berlin noise, I don't remember how we did that. I guess it looks like we just in order to use Berlin noise, I think we just created a random seed, and then we took qualifying random values. That means if the value was actually good, then we did something with it. Random step, there's a jump over here. I guess we could just apply random for now, with a single value instead of multiple values. And that should give us what it is that we're looking for. Okay, so this is now going to be the balloon exercise 2.1. And let's see. So we want to add a wind force that changes over time. So we've already pretty much finished, I think, the update function and the apply force function, because we've been following along over here. And so now we should be adding things together. That makes sense. So what we need to do is we need to create the wind force, which should be something that is done out here. Let's go ahead and create a new function that's just called random wins. And then in here, let's call, I guess instead of having so many movers, maybe let's just have a single mover for now. And I will comment these back in once we get the single mover working. Oh, yes. Perlin noise is very good for terrain. That is a good example. That is a much better example than movement. And it's very useful for generating random nodes. I do agree. Somebody knows their randomness. Okay, so we know that we want to be running these functions on mover. Actually, we won't really want to be running check edges here. We just want to be running show. Let me actually go ahead and rename this entire thing to be balloon. That way we don't confuse, or I guess I'm always a big fan of being more specific where possible. So let's call this balloon, balloon, balloon. We don't need check edges because we want it, or I guess check edges is going to work a little bit differently here. Let's keep it for now, but remove the call inside our draw function. Okay, and then limits, we don't need the limit function. So I'm going to go ahead and remove that. Mover.show, and I believe there's another place that limits was applied, or maybe not. I thought that was done here. Okay. Create a location with an acceleration. We don't actually need an initial acceleration. That is anything that's not 0. So let's go ahead and reset that. And I'm okay with having it start in a random location with 0 velocity, 0 acceleration. I think that's fair. Okay, so we've pretty much just cleaned up how this looks. Let's go back over here and start applying our random win. So we can say let's RNG is equal to random 1. And then let's just do mover, or I guess it's no longer mover, it's now balloon. You know what, I will delete all of these array things. We can add that back in later if we really want to. Let balloon equals new capital balloon. I guess let's let it exist first, and then we do balloon is equal to capital balloon. So now we've just got our 1, okay? And then we want to run balloon dots apply wind. That's going to be RNG. I do suspect we're using Perlin noise the wrong way. Let RNG be apply wind. Oh, apply force. Whoa, that moved really fast. Okay, so I guess we will actually need our check edge thing to make sure it stays within the screen. So let's continue balloon dot check edge. Check edge is not a function. Check edges is a function. Okay, so it looks like it's going really fast. I'm going to just print out what our value for RNG is and see if it's changing every time. I suspect it's not. Okay, so it is changing every time. It does look like it's purely random though. I think there's another way to run actual Perlin noise inside of P5, so I'm just gonna look that up. Oh, there we go. That's what we needed. We needed to run noise, not random. Okay, so what are the parameters that we need for noise? We have x and y, or sometimes space and time instead of 2 dimensions. I believe in order for us to do this, let's see, calculate the coordinates times frame count plus 1,000 or 10,000. So previously when we've done this, we've needed to extract out the noise outside of the setup function. So the noise level and scale, black dot moves randomly on gray square, a hilly terrain. Yes, this is one of the really cool examples of Perlin noise. It's very satisfying. Okay, anyway, let's see what it is that we need to copy over here. Let noise level exist, frame count, noise scale. That's a lot of things. I don't think we need that much. I'm pretty sure we only need let's just copy over this stuff and then we'll use that. Stroke weight, yeah. This is the one we're using. I'm gonna close that one before I forget. Okay, let's comment that out. Let's change this to noise. Actually, we can just move this over into random wind. Okay, there we go. And we'll just accept that as our noise values. Oh, I guess we don't actually need 2 noise things, do we? Let's set times frame count. Okay, so the reason why we need a frame count is because otherwise it's just going to give us one value, I believe. So if we go to console.log noise, oh, not noise, sorry, RNG. Let's remove this. Okay, so yeah, if we give noise a single value, a static value that doesn't move, this is like just asking us, because let's see, what's the best way to describe this? Noise is already, okay, noise as a function, that randomness is done inside of computers is basically just a math function. And there's a whole bunch of math behind this. It uses like calculus and all those good things and derivatives and such to produce a single value in order to make it so that the randomness isn't like all over the place, so that it's actually smoothed out. And so because of that, if we only give it a single value, that's like asking us to plot in a single given point in time where this thing is in the whole like randomness bit. And so we need to add some sort of, I guess like variable that is constantly changing in order for us to actually move along that randomness like map. Like imagine it's like a seismograph, right? And when I say seismograph, I'm talking about like an earthquake line. So imagine that like this actually charts out what our smooth randomness is. In order for us to actually move along this line, we need to actually continue progressing down the x-coordinate. And so the reason why we do that, the way that we're going to do that here is we're going to be using the variable frame count. So frame count is a special variable, and you know that within P5 it's a special variable because it turns pink. that means it's a reserved keyword. And so this variable in particular is attached to, you guessed it, the frame counts. And so the frame counts in this case is the number of frames that our sketch has had since the very beginning. And so if we actually print out frame count instead of RNG, we should see a number that just goes up by about 1 each time. Okay, this is not by 1, because this moves at about, I think, 30 FPS by default, or 60 FPS, something like that. And so it just grabs it whenever it can. And these numbers aren't super precise. Let's see if I stop this. 1, 2, 3, 4, 5. Oh, I guess it does actually move. It does actually catch each frame. Okay, but yeah, the point is that we're actually moving along our randomness, predetermined randomness. Okay, so you may have noticed that when we were running our RNG, that this value, I guess, like, even though these numbers are changing, our ball just keeps getting faster and faster and faster. I suspect that's because we're not actually properly resetting our acceleration after each frame, because otherwise we're never going to like decelerate. And that was like one of the really big things that we were trying to cover. I guess that the textbook was trying to cover. So let's pop back over to Balloon.js. We do actually have the function where we clear the acceleration after each update. So why is it that we keep on moving? One way to clear the acceleration by each frame is to multiply the acceleration vector by 0 at the end of updates. Being able to accumulate and apply forces gets us closer. We're missing the time step. The time step is the thing that I just added in, actually, using the frame counts. This is the rate at which the simulation updates. Usually that is done with a variable called dt, delta time. We're just choosing to make it so that every draw cycle it changes. Okay, so we're not worrying about that too much. Floating upward, bouncing off the top window. I guess the other thing we will need to do is actually we need to make sure that like when this thing bounces off the top, it doesn't actually respawn like the way that we've been doing it. So yes, let's go ahead and do something about that. Oh, I guess the other thing is that technically speaking, RNG, the reason why it's moving all the way to the right and it's not moving up and down at all, there's no Y components to this, is because we're supposed to be applying forces, but instead of applying a force, we're applying a single value. And so I guess JavaScript is doing its best to convert that single value into the vector that we need. And the vector that we need is supposed to actually have two components, x and y. Because x comes first, it just assumes that this first value is going to be the x value. So let's actually hop in here and make it so that this is a proper vector instead of just a single value. So inside of noise, we're going to, or around noise, we're going to create a vector. And we need to give it two values. So let's go ahead and we can grab the same noise right here. And we're just going to add an offset of like 10,000. When I say offset, that's because technically speaking, we're taking the same random seed, so to speak, and we're just saying 10,000 frames later is where the y value is going to start, and that's random enough for us to work with. So let's go ahead and see that. So now we've actually got some y components moving. Oh, welcome to the stream, Domosaurus. Sorry you missed the first hour. Let me share the code that we currently have, and That should help get you caught up to speed. Okay, and as far as the part in the chapter that we're on, we're at exercise 2.1 inside of chapter 2. You can find the link to the book inside of the Discord announcement. Okay, so let's see. Right now, we've now added in our RNG vector, so now we're applying it, and so we've got the x and y vector that's moving fast and fast and fast. Okay. So it's still disappearing off the screen. Let's make it so that the noise for the y value is actually negative. That way it moves in an upward direction. Okay, so now we've got it moving in an upwards direction. Let's make it so that whenever it hits the top part of the screen, we reverse the acceleration. Just for a little bit and see what happens there. So first off, this dot position.x, this is the left and right bounds checking, and so that means this must be the top and bottom bounds checking. Happy to help, Dominosaurus. Okay, so we've got the top and bounds checking, and so when this dot position.y is greater than the width, okay, so I suspect the reason why it's using width here is because we're taking advantage of the fact that this canvas is a square, and so the width and the height are technically the same. I say whoever wrote this code as if it wasn't me. I was definitely the one who wrote this code. That was just from a previous workshop. Okay, so now we've got the proper variables. We still want to make it so that instead of the y position changing, what actually happens is we have it so that the acceleration gets reversed for a little bit. Acceleration, I guess maybe we would want to actually just apply the force in a different direction. I'm not entirely sure what the best way to make it bounce is, actually. Let's go back up to our lovely definitions over here. Which definition, which of Newton's laws is most relevant here? Equal and opposite reaction. Force is equal to ma. Object in rest stays at rest while an object in motion stays in motion. I suspect that I'm going to move this over, actually, that we have more screen real estate. I don't know why I didn't do that sooner, because we don't actually, this is actually properly, mobile responsive. Okay. So I guess we can try doing both acceleration and velocity multiplication on the check edges to just get it to move in the opposite direction. I'm still not entirely sure why our apply force isn't quite working the way that we need it to with this whole, oh, it's probably because acceleration is in the wrong spot? No. Create vector, apply force with the wind. Apply force is only the acceleration adding. And then we also remove the acceleration after it's been applied. And we initialize the acceleration and velocity to be 0 to start with. Okay, I guess let's actually worry one thing at a time. The only thing we're worrying about right now is whether or not this thing bounces off the top. So I guess instead of this, let's actually have the acceleration, this dot acceleration dot molt, and let's just make it -1. I guess all of our vector math is going to require some sort of a force. So let's actually make this a create vector. Create vector. Maybe it's better to actually extract this out into its own variable. So let's opposite vector equals create vector -1, -1. And then we'll just plug that in right here. Else if the position is less than 0, if it is less than 0, that means it's actually over the top. Oh, I guess we put this in the wrong direction. Let's actually move this down here then. Okay, this dot position dot y is equal to height. Is equal to 0. Still not moving in the direction that we needed to. Top and bottom bounds checking. If this dot position dot y is greater than y, yeah, so that's the one where if it starts off too low down here, then we would pop it off at the very top. Start it off at the top. And then if it is less than 0, that means it's gone over the top. So then we have our opposite vector, and that didn't seem to work. I guess instead of molds, what would make sense here? Would it just be to add? Well, that just kind of left. I am kind of struggling with this. So for the sake of time, let's go ahead and take a peek at what the proposed solution is here. The nice thing about this textbook is that there are proposed solution or suggested answers. Let's see what it is that they did that we were unable to figure out. Let's go ahead and run this just to see what the example would look like. Okay, so we've got a lovely balloon and it's moving to the left and to and it's just stopped bouncing. Okay, so let's actually start deconstructing how this thing works and see if we can copy it in some way. Start by looking over here to see if there's anything crazy that we should have done over in our starting sketch. So let's say, it looks like the wind was actually done outside of our sketch function. But other than that, no, nothing too crazy. I mean, we created a balloon and this time looks like we gave it a starting width and height. So that means it should start in the bottom right corner. Yep. Okay, now let's pop over to balloon.js and see where everything changed. Okay, so I'm going to start by just hiding all of this stuff over here. So the show function is just going to draw the actual balloon, so we don't need to worry too much about all of this stuff. Basically, that just allows us to have a balloon, or something in the shape of a balloon. Let's look at check side, since that was the function that we were kind of stuck in. So instead of check sides, we call it check edges. Doesn't really matter. There's the left and the right bounds. And then we just changed the position to start on the other side of the screen. So if it went too far to the right, aka above the width, then we reset it on the left side of the screen. Okay, that's, we had that. I guess should bounce is the thing that we got stuck on. Return this dot position dot y minus the diameter divided by 0. So how is this function used right here? Returns true if the top of the balloon has exceeded the top of the canvas. Okay, so that's just letting us know if the balloon has gone over. So then I guess check edges didn't need to actually be responsible for the top and bottom bounds checking. Okay, so I guess the juicy bit is probably going to be under apply force. No. Apply force we have basically the same thing. So I guess all of the juice is actually under update. Okay, and that is a pretty big function. Let's go through this. I'm going to just full screen this. Is there an easier way to full screen the code side? I wonder. Doesn't look like it. Okay, so let's go ahead and do that. Yay. Okay, so check to see if the balloon has hit the ceiling. If so, send it backwards. So we have a function to check to see if it should bounce. And then the actual action that we took was to reset position.y so that it's below. Okay, so I don't think this change is going to be that big of a change. Loses speed when bouncing. Okay, that makes sense. Apply helium and wind forces. I guess what we should have done is we should have had a separate force for the upward force, and then a separate force for the actual direction. We got caught up doing just the direction of the wind. Let's see. Wind map. Wind X is we mapped the noise between 0 and 1 to between negative 0.01 to negative or to positive 0.01. So I guess the map function, if we haven't seen that before, basically makes it so that if we took, or I guess it takes the first parameter right here, whatever the value is right there, however far it is from the left and the right bounds of the next two values, which in this case is 0 and 1, because we know that noise is always a value between 0 and 1. It is going to remap that to be a value that's between these two numbers, so something that's much, much smaller. Okay, and then create a vector using the winds, and then with no y component. That makes sense, because otherwise it'd be pushing more and more up. Okay, and then we just apply the force there. Okay. Then velocity.add acceleration, velocity.limit. So I guess we should have kept the limit function here. Position.add this velocity, check sides, acceleration multiplied by 0. So that's where they actually reset the multiplication, and then added the noise afterwards. So this is, instead of doing the track frame for the noise, we just added in a 0.01 for the step for noise X. Okay, so let's go ahead and start working on adding those changes to our code. So I'm going to go ahead and chop this off. We're going to, I think what we'll do is we will copy over the naming convention of check sides to extract this out. And then so wherever, or I guess we can keep this as check edges for now. And then let's add in a function to, let's see, what's the best way to do this? I guess we can just hop into doing the update function now. Check if it should hit the ceiling. If this dot should bounce. I guess there's two ways for us to go about this. One is to simply to try to adapt the balloon code to what it is that we have. Or the other option is to take the example code and then extend it out to be something different. So let's see. I think it would be pretty interesting to make it so that extends this thing out so that we had a whole bunch of balloons bouncing around. But that doesn't actually help teach us anything. So what I'm going to do is I'm just going to continue trying to adapt this code to the examples that we had. Okay, so let's go ahead and continue doing that. Let's add in a function that's called should bounce. This is the thing that is going to return some sort of a true statement. Okay, let's also extract out the random wind over here. I think, let's see, how does check edges done over here? I don't believe it was done outside. Yeah, it's not done outside. That's okay. We only need the update and show. Let's go ahead and keep that as is. Update should bounce. This doesn't do anything right now. Okay, so what we want to do is we just want, for should bounce, is we just need to see if the circle is close to the top. So the way that circles are drawn inside of P5, I believe we're doing a circle, right? Yeah, this is done using a circle. Is we basically take our circle and the point of origin is actually right in the middle of this circle. So it's something like this. So if we want to see if this thing is near the top of the screen, what we actually need to do is we need to take the distance. We need to take this distance, which is the radius. Whoa. Which should be the radius. And then we need to add that to whatever our current x and y location is. I guess in this case, it's just the x location. Or sorry, the y distance, which is how far we are from the bottom of the screen. So if we do r plus y, that should tell us whether or not we're at the top of the screen. So let's pop back over here. And then so we do if this dot y plus, or this dot position dot y, because position is where we actually are in the world. And then we add this dot, I don't know where the r is defined. It looks like we just did a hard code right here. So let's just go ahead and make that into a variable right here. We'll call this the radius. Is equal to 48. And then we can replace this dot radius. So the reason why we're doing that is so that we can actually grab onto this radius outside of wherever it is that we've defined what our circle looks like. So now we can do something like this. I guess let's just have this return true always for right now. So we've got, this is the current location of wherever it is. So let's go ahead and put that into a dedicated variable. This is not something that changes between each time we call should bounce. So I'm going to put this into a variable or a constant that just says position is equal to this dot position. Maybe not position. Let's just call this pause y, position y. So then we have position y. If position y is greater than 0 minus this dot radius. Is that right? If position dot y, it is greater than 0. No, if it is less than 0, that means it is above the screen. Then we need to remove it, I think. Let me make sure I'm getting my math right. So if these two are above 0, that means we need to add it back in. But we actually want to do that before that happens. So in this case, what we need to do is we need to track to see if okay, so this is the bound at 0. So then, technically speaking, what we need is the hard-coded value of r, just radius by itself. If it is less than the radius, so then instead of that, if it is less than the positive radius, then we need to make sure that we actually, this is where we need to return true. Otherwise, we will return false. I think that makes sense. Let's see if we got that right. Should bounce. Minus diameter divided by 2, and the stroke weight. I think, I guess we should add the stroke weight. This dot stroke weight. Okay, so we did it in a slightly different way. I don't think that's going to be, what happened to our circle? Oh, it's just on the right side. Okay. So we've got should bounce. And then if it does bounce, what was the thing that we needed to do? We needed to reset position.y so it's below the ceiling, and then make it lose speed. Okay. This dot position.y is equal to this dot radius I guess we're just resetting it back to wherever the radius is, plus this dot stroke width, or stroke weight, not width. Okay, so this just resets. And then we slow it down, so that is this dot velocity dot y times equals negative 0.75. Okay, that makes sense. We need to actually have the upward force now. I'm going to remove those comments. Okay. This dots apply force. This dot helium. So I'm assuming helium is defined up here. Helium is a small upward only force. There we go. Sure, let's do something similar. Okay, so this is moving it in an upwards direction. So then if we pop it over here, we can apply this dot helium. Okay. And then now we want to actually apply the sideways force. So this is where I'm going to actually put it outside of this function. And we're going to be a little bit more different because I think this will make it a little more readable. So let's pop in over here. Let's just call this wind force. Or I guess this dot wind. This dot wind. Sure, we'll just call it wind force for now. Okay, So let's see. Did we already remove all of that? Yes, of course we did. Okay, so what we did previously was we had, I guess like wind x is equal to, we'll go ahead and copy over what he's doing over here. This dot, or what the author of this did. This dot noise.x. Instead of doing this dot noise.x, I'm just going to do what we did before, which was frame count. And then we'll keep the values that he had that were listed over here, which is 0 to 1 because noise is between 0 and 1. And then we're remapping it to that. Let wind is equal to create vector and x 0. This dot apply force, this dot wind force. I guess we would need to return something here. Return wind. Okay, maybe let's just call this wind. Wind. I think that looks nicer. Okay, so now let's look at what it is that we have. Should bounce. It should be this dot should bounce. Circle was expecting a number for the second parameter and it received 0 instead, or not a number. So I'm guessing that's because this is the value that got messy. It received a string instead. This doesn't look like a string to me. This dot radius, how curious. For the first parameter, so this dot position dot x somehow became a string. I'm not entirely sure what happened there. Well, it must have been something we've done. So let's look at where position has been used. Position, position, position. Wind x, check edges. Position dot y. We don't even touch position dot x. I'm assuming by first parameter it's actually talking about maybe it's happening over here. Noise, frame count, create vector, apply wind. Line 40. Position dot x, position dot y. Am I spelling position wrong? No. If I put this back at 48, does that fix everything? It doesn't. Okay, so that's a relief. It's not something that I added in that area. This dot position. So why is it the position dot x is not a number? Maybe it's because we broke position somewhere. Should bounce. This is definitely not going to be a problem here. Let's look at where we were using position. I think we've always been tossing in real numbers. Random width, random height. So it should be given an actual value. This dot should bounce. This dot helium, this dot wind. Hmm. Why is it set to 0? Let's just try starting to spam the console logs. This is really curious. Why is it saying that wind is so weird? This dot apply force. So hang on. If I just commented out wind, does this work? It looks like it's working. Nope. We still overwrote position somewhere. Okay. I'm not sure how much value we're really adding by digging this much into it. So what I want to do is I'm going to hop back over to the example. And let's see if there's anything we can change here instead of, I guess, updating our version. I guess the only thing we could really do is make it so that like that would be interesting is maybe we should just continue going through the textbook. So that's what I'm going to do. I'm going to continue going through the textbook, see if we can get something more interesting out of the next exercise. I think we were able to eventually figure out what was going on. I think we have an idea of what this should have been doing, at least. We just didn't have a very good implementation of it. Okay. Units of measurement. This is a heads up on making sure that we are... Oh yeah, there's no mass within P5 necessarily. So we can make our own version of mass. So we're going to be tying mass to pixels. That makes sense. The more pixels it has, the more material, so to speak. That's also assuming that every single thing that we make within P5 is going to have the same density, but in real life, things can have different levels of density. That is fair. Mass is a scalar and not a vector. It is just one number describing the number of matter in an object. It is simpler to begin by saying, hey, the mass of this object is just an arbitrary value. Okay, that is fair. I wonder... Maybe we should just try to finish this. I need to... Because It's going to be kind of hard to actually make use of any of this other code if we don't have a working thing to play around with. So I'm going to continue digging into why we are getting a nan for our circle over here. I don't know if at this rate we're going to be able to actually finish this chapter within next stream even. We've only got 30 minutes left, so do let me know in the comments if there's something that you'd rather see me try to do on stream rather than debugging this very silly problem. Okay. So for some reason, our position.x. Maybe it's because our position.x just became like inhumanly large or incomputably large. Or maybe it's not even an x thing because we don't even adjust the x value at all, do we? Position.x. Yeah, we don't really adjust that. Maybe it's our should bounce function. Let me remove this. Oh, wow. Okay, so it is indeed our should bounce function. So something we did there is what actually broke everything. Let's see if our wind works at all. Was expecting a number for the first parameter, but received a string instead when we applied this dot wind. Maybe I'm just really bad at figuring out how. Okay, let's start over again. We've got an update function. This dot should bounce. Let's pull up the should bounce section. So we don't care about that. We don't care about check sides. This dot position dot y is less than 0. I guess, okay, maybe let's start by updating this. This should just be return this dot position dot y plus. Let's stop this from running because it seems like it's having a heart attack. This dot radius, because we did radius instead of diameter. We're not going to worry about stroke weight, so let's just set that to be that. So we're not going to worry about that. Okay. And then we can run this. I'm going to toggle out the wind. Let's toggle out this as well and just see if it works. Okay, so it runs without that. So we know something that we do here breaks it. Position.y. Maybe it's because stroke weight is a bad value. Okay, so stroke weight indeed was a bad value here. So for some reason, helium isn't actually applying any force right now, which is strange because it should be moving in an upwards direction over here. So that means something else isn't working. Because we haven't even gotten to wind yet. Maybe it's, I mean, this dot apply force doesn't really have that much going on. So I suspect that's not the problem. It must be our update function. Apply helium. Velocity.add acceleration. We aren't worrying about the limit right now. This dot add velocity, so that's the thing that actually moves us. Maybe it's because their acceleration is just constantly being reset to 0. So if I remove this, is it going to start moving again? No, that didn't change anything. Hmm. This dot apply helium. Helium is just a normal math function. Yes. Is it because there's something I'm not doing here? Update and show. New balloon. No, we've pretty much got the exact same thing going on there. Oh, I guess this is the reason why we were having issues earlier. It's because I didn't realize that they were setting stroke weight like explicitly over here. That is embarrassing. Should bounce. Still position Y, and then radius. Plus maybe this should have been negative. I don't suspect that would actually change it. I think for now, I will figure out what's going on with this thing off stream. And then when we come back next, I think tomorrow, I will explain what it is that I was able to discover. For now, we're just going to continue as if we're making a copy of this. So one nice thing is that within the P5 editor, it's really easy to make a duplicate of something. All I need to do is, once I'm signed in, is just save this thing as myself, as my own thing. I'm just going to leave it as copy so I know that I have the working solution. And we're just going to pop over here and oh, where did this come from? Oh, there we go. Okay. We're going to... Maybe we should go back to this. Or I guess... I'm so wishy-washy on this right now. Let's go back here. Because I kind of want to have the mover that's right here. Let's just continue going through this. Okay. So we've got the mass. Force divide by the mass. And we add in the force. So I believe when we do the mass division, that is in reference to, let's see, multiplication. A vector multiplication would be, I guess, like making it longer. So I guess making the force longer. So then I guess the mass is reducing the amount of force that it's applying right here. Since it's a scalar. Scalar being the magnitude, even though the code looks reasonable, it adds a major problem. Consider the following, both being blown away by the wind force. Mover A, mover B, let wind, create vector. Okay, so yes, they both have the same thing. Where is the problem here? Imagine you're the computer, mover A receives the wind force of 1, divides it by the mass, and adds it to the acceleration. Okay. Yeah, so we reduce the wind force by the mass. Then we move on to object B. It also receives the wind force. So the problem is that the wind force is, I guess, like the global thing instead of it being a per object force right now. And so that's why we ended up with a 0.01 or 0.1 on mover B instead of the one that we were expecting in mover A. So let's see. In this case, we just need to find a way to protect the original vector and make a copy of it before dividing the mass. That makes sense. So we have a convenient way of copying vectors. Force.copy. So when we apply the force to a different vector, we just need to make sure that we copy it and then multiply it, or yeah, divide it by that. Okay, that makes sense. Let's take a moment to recap what we've learned so far. We defined a force as a vector. We've shown how to apply the force to an object divided by mass, add it to the acceleration to, I guess, make it feel more weighty. This is the resistance that a stationary object applies. What is missing? We need to figure out how to calculate force in the first place. Where did the forces come from? We could write apply forces in another way using the static method divide instead of copy. So then his recommendation is to rewrite apply force by using the static method. For help with this exercise, review static methods here. And I believe that is, this is just going to be like a programming static versus non-static methods. So the way that static methods works, I believe, is if we had just done it using, I guess, like the straight values instead of using it with the vector values. Oh, these static methods allow you to perform mathematical operations on vectors without changing the value of the input vectors. So then where is the non-static methods? Because random 2D is a static method, meaning it's associated with the class as a whole rather than individual objects. Oh, it's talking about like object-oriented static versus non-static methods. Okay, that makes a lot more sense. Rewrite apply force using the static method. So then using the static method divide instead of copy. Let me open up a whiteboard for this. Apply force. Let f is equal to something. This dot acceleration dot add f. So in this case, this should be force dot you could write apply force another way. Hang on. I'm not entirely sure what it's asking for right now. I'm just going to reveal the answer. Vector dot, oh. Yes, that makes sense. Okay, so the answer ended up being p5.vector.div because vector is the overall class, and otherwise we would be doing something like force.div instead of vector.div. And so if we applied it to the force.div, then that would change what would that change? I guess. Oh, okay. So the way that the div usually works is we would have a existing vector over here. So this would be like vector1 dot div, and then we would just take in a single parameter, which would be like a second vector. And then so that would be equivalent of defining the first vector by the second one. And so in this version instead, we have two different vectors as parameters over here. So in this case, it would be force and this dot mass. Okay, that makes more sense. To me at least. P5 dot vector dot div vector1 vector2. Okay, so that's what the difference between these two are that he's highlighting. Oh, hey Freddie. Thanks for tuning in. Okay. So continuing on, creating forces. This section presents two ways to create forces in a P5.js world. We can make up a force, we can add in whatever forces it is that we want, or we can model existing ones. To begin, we'll start with the first approach. And so we can just pick any two numbers that we want, and we can start with simulating wind. How about a wind force that points to the right and is fairly weak? Assuming an object mover, the code would read as follows. Winds create vector with a right direction of 0.01 and no up direction or no y direction. We just apply the force. This isn't terribly interesting, but it's a good start. We've created a vector object and passed it to the mover object, which in turn will apply its own acceleration. To finish off this example, we'll add in gravity and gauge the force only when the mouse is pressed. Okay. So let's see. Now that we have two forces pointing in different directions, both applied to the objects, beginning to get somewhere, we built a world where an environment with forces acts on objects. Look what happens now when I add a second object with variable mass. Again, I'm not covering all the basics here. That's okay. I want to skip to what it looks like with different masses. Okay, that is kind of funny. And then we apply the wind. Now, of course, this simulation, we're not actually adding in anything with air resistance, so these guys will just keep bouncing on forever and ever. Okay, now let's actually look at what it is that the author has added. So we initialize the constructors to 1. We apply the force, receive a force, divide by mass, add to acceleration. And then we update, pretty standard stuff right there. Scale the size according to the mass. And then we decided to make it bounce. Nothing crazy there. And then we have a second one, and then every object has a mass of 1 and a position of blah, blah, blah. So this is basically just, we're adding in arguments to the constructor so that we can have two different sizes. That makes sense. Okay, so I guess that is something that we can try doing with the example that we had earlier with the, where is it? So let's go ahead and try doing that. We're going to take the solution copy that we had earlier. And let's see if we can add mass to this. Well, 5 minutes. I don't know. We don't have a lot of time to really do anything super interesting in these 5 minutes. So I guess what we can do is when we pick up on this next, I guess tomorrow, we can do that. Okay, hopefully we'll get further when we do this tomorrow. I guess I'm just gonna start wrapping this thing up. We're gonna wrap up a little early since we're at a pretty good stopping point right now. I want to give a quick shout out to the next workshop, which is going to be the Static to Interactive Web Dev Part 2 workshop. So if you want to tune into that, it'll be another couple of hours. Is this the right one? 7 to 9 p.m. Eastern Time. And that is 3 hours ahead of where I am, which, yes, that would be 4 p.m. my time. Okay. So, yeah, make sure to tune in to this next workshop. And who is this with? This is, if I remember the Today in Global Hack Week, I think the Static to Interactive, that's done by Farshini, I want to say. Anyway, send them some love for me. Thank you so much for tuning in, everybody. I will see you all tomorrow or somewhere on the Discord. Really appreciate the message. Yes. Good luck with going through it. And good luck going through the exercises. I think they're a lot of fun. And if you do get stuck, you can always do what it is that we did on stream, which is take a look at the example and try to see where it is that you got stuck. Hopefully, I'm going to figure out where what it is exactly that happens with our copy of the balloon. And I'll bring that up. Yes, keep the pizza going. All right. Toodle-doo, everybody. Until next time, stay warm and cozy. All right. Bye.